Our energy needs are evident everywhere, from the lighting and the air conditioning in this room to the fuel that powers our cars and our aircraft that brought us here today. And it's been estimated with industrialization and with population growth that the energy demand over the next 20 years is likely to increase by 35% or more. So where are these energy resources going to come from? They're going to come from areas like this. And a large fraction of the energy that we require may come from non-traditional sources, subsurface sources from areas in Australia and around the world. So what kind of resources are we thinking about? Well, in Australia, we've had a lot of publicity recently about coal seam gas. In North America and Europe and elsewhere, shale gas is a very big potential resource. The geothermal sector has been developing very steadily and in the last few years very spectacularly, and that presents a very large potential energy resource. And as a consequence as well of this energy and the carbon outputs, we may also think about what we do with the carbon dioxide and putting it back in the ground. One of the key questions in this industry sector is to be able to effectively monitor the movement of fluids and the movement of water and the changes in the earth as these energy resources are developed. And we need a cheap, essentially a surface measurement technique that can image changes in the earth. So, what am I talking about? Many of you will be aware of the term fracking. It's been in the newspapers, it's been on TV, it's a very emotive term at the moment. In an engineering sense, fracking is the movement of fluid mixtures and pumping of fluid mixtures down into the earth, into sequences such as shales and coal, or deeper into geothermal areas, maybe thousands of meters down. And for the shale gas and for the coal seam gas, the movement of fluids and the fluid mixtures release gas that can be extracted. And for the geothermal sector, the fluids heat up and be transferred back up to the surface to bring the heat back to the surface. So we're looking at scales here of tens of meters down to potentially thousands of meters down, in which we're making a change in the earth that we can't actually see. So we need a technology that will allow us to see into the earth. The key issue, and the key word here, is permeability. The permeability is the ability of fluids and gas to move through the earth. And what we're doing in a fracking experiment and a fracking procedure is changing the permeability. It's allowing gas to come out, it's allowing fluids to move through. So permeability is one of the key features that we'd like to know something about. The current state of the industry, and an excellent technique that is used globally, is a method called passive seismics. Now, in this diagram here, each one of those little dots represents a small earthquake. And for those of you who felt the earthquake in the hills on Tuesday, that was a magnitude 3.3, these earthquakes are magnitude -1 or -2, so something like 10,000 to 100,000 times smaller than the one we had in Upper Sturt this week. But what they do show is when you pump fluids down into the earth, where does the earth crack? This is an image from Geodynamics, who are a geothermal company exploring in the Cooper Basin, right in the centre of Australia. Pumping fluids down, you can see where the earth cracks as a result of that stress. But there are three problems with this approach. Firstly, where the earth cracks is not necessarily where the fluids flow. So we don't know necessarily that this is a map of where the fluids are connecting. It's just where the earth is breaking. Secondly, it's quite an expensive method if you require a second observation well. And you sometimes do if you want to monitor changes both spatially and also vertically. And the third aspect is this works very well for many situations, but it's not overly apparent that it works necessarily for regions like coal, which is a lot softer material. It doesn't necessarily break to give a little earthquake. So what can we do to as an alternative approach, the University of Adelaide group works with electromagnetic geophysical imaging equipment. And the ability of electromagnetic measurements is that they measure the pathways of electric current through the Earth. And fluids conduct electricity. So what we can do with electromagnetic instruments is to be able to determine something about the fluids and also the connection of those fluids in the ground. So what we've developed at the University of Adelaide is a very novel electromagnetic instrumentation, some data processing methods to take that data and turn it into something we can interpret, and in particular the approach of what we call 3D, which is imaging structure down in the ground in all dimensions, but also 4D, which we might think of as time-lapse, that is a change in the Earth. So I'll show you some examples. We're working with Petrotherm, it's a geothermal company in the northern part of the Flinders Ranges. They're developing a geothermal resource at a place called Paralana. They're pumping fluids in at a depth of 3.8 kilometres. And just to give you an idea of that scale, the distance of 3.8 kilometres is from the very northern part of North Adelaide to the middle of the South Parklands. So think about that distance and turn it into a depth. They're pumping fluids into that point to heat up those fluids. We've been monitoring and measuring in that environment for some time now, and I won't talk to you too much about what these diagrams mean, but just to say they show the response of our sensors on the surface. So in the top diagram, our sensors have a certain bandwidth, that means they measure different frequencies, and on the x-axis, if you like, the time axis, that shows the change with time. The blue parts basically show no change, and the yellows and greens show a change. Now, what I've shown here is that a particular bandwidth of our signal, that is a particular frequency range of our signal, we see change in the Earth. And that change at a certain frequency corresponds to change at a certain depth. So what we have the ability to do is to show change in the Earth even at a depth of 3.8 kilometres, which is a lot deeper than most of the energy resources that we might look at in, say, coal seam gas. So taking that data and turning it into a structure of the Earth, this diagram basically shows depth on the left-hand side, going down to, in this case, 5 kilometres. And I've just colour-coded it from the orangey yellow colours of sort of basically lots of water, connected well, down to the darker colours represent zones of the Earth that have very little permeability. Now, the dashed line basically shows where the water was pumped down, and what we show is that you can see the changes in permeability occurring at 3.8 kilometres. This is really right at the limit of what we can detect with our instrumentation, but still, think about the distance and that distance down. It's a powerful way of determining not just where the Earth is cracking, but where the fluids are connecting together. So our methods are very much sensitive to the fluids and the permeability. So in terms of what the university has, in the University of Adelaide Geophysics group, we're developing technologies. We're developing very small, rapid instrumentation to monitor big fields, whether it's CO2 sequestration, geothermal, potentially coal seam gas, shale gas, and others. We're looking at being able to map water, map fluids, and map the connection of those fluids. And we've done that for very deep systems. And in particular, one of the main aspects is it allows us to look at three-dimensional and time-lapse, those four-dimensional change in the Earth. So it's a powerful means of monitoring energy systems. So, our group has been developing these technologies for some time, and what we're looking for at the moment is partnerships. We're looking for partnerships with industry to develop these technologies to the point where we can demonstrate that they work very effectively for many of the energy resources that we are currently developing. We have licensing opportunities for the equipment we're developing, and we're seeking opportunities to further refine and develop and take to market readiness some of the software and the hardware that we're currently working on. Over the next few decades, in Australia alone, the number of boreholes being drilled for these new energy resources is in the tens of thousands. Globally, it's hundreds of thousands. We believe the University of Adelaide Geophysics group have the ability to provide some new science for the monitoring and the effective development, both in terms of economic, social, and environmental monitoring of these new resources. So we think there's big opportunities in what will be a multi-billion-dollar industry. Okay, thank you very much.